should be good. Okay, and yeah, so we finished about our query algorithm, talking about basic quantum algorithms, and now we are going to talk about one of the very important quantum algorithms, that's quantum Fourier transform. So we will actually go away from our quantum query world a little bit and go to talk about this quantum Fourier transform, which is just a quantum algorithm with usual input and output with all the black boxes. Okay, and this is in chapter 5. And yeah, this is a very important quantum algorithm because as you might know, that this will lead to this short factoring algorithm, which is what led people to believe that quantum computing has exponential speed up that's very useful for real world application. Okay, so we are going to build from quantum Fourier transform and see that how you factor a number really fast on a quantum computer. Okay, so yeah, so that's the scope. This is all told in chapter 5 of the book. And let's start with a bit of a review on Fourier transform. Okay? And yeah, so this is the quantum Fourier transform will be generalization of the so-called discrete Fourier transform. Okay? So if you properly learn Fourier transform in the signal and maybe in a signal processing course, there are actually many different forms of Fourier transform. And yeah, so I think maybe some of you have learned a continuous version of a Fourier transform where you have a continuous function and then you Fourier transform to another continuous function. Okay, but what we are doing here is the discrete version of Fourier transform. So we are just transform a discrete set of a number to another discrete set of number. So we just basically we can think of this discrete Fourier transform as transforming a vector of n dimension to another vector of n dimension. So we start with x and go to some y. And it's going to be a linear transformation, so you can just write down it as a matrix. Okay, so this discrete Fourier transform can be just described by some matrix Fn here. Okay, so I should put it red, but this Fn is our discrete Fourier transform. So you multiply this matrix Fn on your input vector x, then you get the output vector y. It's quite straightforward. And what's Fn? Fn is written here. Okay, so so discrete Fourier transform actually will be a bit different for everyone, but they all have a similar form. Okay? So n-dimensional discrete Fourier transform, you can just write down the matrix element of this Fn, and it is 1 over square root n, so some normalization. And this is a really interesting complex number here, so you have e to the 2 pi I jk over n. Okay? And I guess it's easier to see an example first. So what does this matrix look like for different n? Okay, so for F2 you have actually a very familiar matrix we have. So I guess okay, so this thing is quite a mouthful, but you look at this. So this thing is e to the 2 pi I over n, which is the nth root of 1 in complex plane and to the jkth power. Okay, so you can read this part as this thing. Okay, and so try to read this. Then the first thing you need to think what the e to the 2 pi divided by n. And when n equal to 2, then e to the 2 pi divided by 2 is just 1 and minus 1. So the 2 roots of 1 in the complex plane. And then you have it to the jkth power. And so those k and j are just indexed here. So for example, this is 1, 1. Oh, sorry, and k and j. And here, k and j are a little, I guess, rho k. Okay, and it's the convention is a little different. Okay. So k and j is row number and the column number, but usually here we don't want to index from 0 to 1. Okay, we don't want to go from 1 to n. We actually want to go from 0 to n minus 1. Okay, So this fnkj is the element of row, actually row k plus 1, and so this should be k plus 1, and column j plus 1. Okay, for your n by n matrix, because you want to count from 0 as we see here. So we have x0 to xn minus 1 and y0 to yn minus 1. So we have we have nicer thing here. Okay, so here we have kj, and which one is k? Okay, so this is k equal to 0, k. Oh, sorry. So too many wrong direction back here. Okay, so here we have this is the row of k equal to 0 and k equal to 1, and here is a column of k equal to 0, k equal to 1. Okay, so for f2 this e to the 2 pi I over 2 equal to minus 1. So we have minus 1 to the 0's power those 1, and the minus 1 to the 1's power is this minus 1. And it's normalized by this 1 over square root 2. Okay, and it's this Hadamard function, Hadamard matrix, as we talked about before. Okay, and then f3 we have omega don't have a nice name, is e to the 2 pi I divided by 3. Okay, so in complex plane it's this point. So you have real and imaginary, and then you can think about this unit circle. And so you have 3 root of 1, so 1 is third root of 1, and then you have this omega here and omega square here. Okay, and so this angle here is your 2 pi divided by 3. Okay, so you have 2 pi divided by 3, and also 2 pi divided by 3, and 2 pi divided by 3, and they are 120 degrees. Okay, so this point on complex plane is omega. And f3 you see has a very also very symmetric form around omega. So once again, if you count, okay, so it's very crowded here. So let's erase that and rewrite. So you have the row number 0, 1, 2 and the column number 0, 1, 2. Okay, and so first column and the first row you have 0 multiplying something, because you want it to be the jk's power. So because you are multiplying with 0, so all these are all 0. And then on this column you have 0 times 1, and you have 1 times 0, and 1 times 1, and 1 times 2 power of omega. So you have omega to the 1, 2, 0, 1, 2 power. And here you have 2 times 0, 2 times 1, and 2 times 2. So omega to the actually 2 and 0 to 4 power, but omega to the fourth power equal to omega to the 1th power, because omega to the third power equal to 1. So you also have omega here. Okay, and then yeah, for similarly you have omega equal to e to the 2 pi divided by 4. Now it's just this imaginary point here. Okay, and maybe let's draw a picture also. So for n equal to 4, you have this thing equal to this point, and we have these 4 roots. So we have I and minus 1 and I. Okay, and yeah, so omega equal to I, and we have omega square equal to minus 1, and omega third equal to minus I. Okay, and so once again we can label this with our j and k, and j k should go from 0 to n minus 1, so 0 to 3, so 0, 1, 2, 3, and 0, 1, 2, 3. And so you see on first row and the first column, because you are multiplying with 0, they are all going to the 0's power, so they are all 1. And so here you have I to the 0, 1, 2, 3 power, and here you have I to the 0, 2, 4, 6 power, which is equal to 0, 2, 0, 2 power. And on the left side you have I to the 0, 3, 6, I think it should be 0, 3, 6, 9 power, and actually equal to 0, minus 1, minus 2, and minus 3 power. Okay, so yeah, so those are the matrix for discrete Fourier transform. Okay, so you see that it has a very how should I say, very symmetric form here. Those all the term inside are omega to some power, and with some increasing sequence to on their powers, because it's just omega to the jk's power. Okay, so that's the matrix, and for our convenience, yeah, so this is just define the discrete Fourier transform, and we are going to say some property about it. And one thing we'll say is we would like another expression for just writing down discrete Fourier transform is because it will be nice for when to do our calculation is you can ask what's so if you think about you apply fn on some x, get some y as output, then you can ask what are each element of y, what's the expression for each element of y, so what's the case element of this y, then it can be written as some linear combination of this input of this element x. Okay, and so basically you do matrix multiplication, and you see that the case element of y will be this basically I guess it's easier. I still like to write down. Okay, so this y vector equal to this fn matrix times this x vector, and so you ask what's the case element here, and that should equal to just this case row here in the product with your x. Okay, and so case row here is okay, it's actually not case row, actually k plus row, because we count k from 0. It's a bit confusing here, and but this yk should be just this fk row, which is e to the 2 pi I, and e to the 2 pi and to the kj for difference j, and the inner product with your xj. So it's this summation, then you have this normalization 1 over square root 10 xj times e to the 2 pi jk over n. Yeah. And yeah, it's actually a symmetric matrix, so kj row and the jk row are the same. Okay. Okay, so those are discrete Fourier transform, and we can write down the element-wise expression here. So it's a nice expression to know also. Okay, so this expression will be used a little bit later. Okay, so any question on the definition of a discrete Fourier transform? If okay, then yeah, let's talk about some property of a discrete Fourier transform. Okay, so we can think about discrete Fourier transform. Okay, so we have some example of the matrix, and we have some example of what happens when you apply the matrix, and this property will be actually quite important, so nice to remember that. Okay. And the property basically comes from this thing. Okay, and yeah, the property comes from this fact that when you have n different roots of 1 on this unit circle, so you think about nth root of 1 on convex plane, then there are n roots. For example, n equal to 5, you have those 5 roots here. Okay. And then if you add those 5 roots together, they will become 0. Okay. So that's an important thing to remember. So if you add all the complex roots of 1 together, no matter what n is, you add them together equally, then you will become 0. Okay. So here, I guess I can write, so this omega phi to the 0 plus omega phi to the 1 plus omega phi to the 2 plus omega phi to the 3 plus omega phi to the 4 will equal to 0. Okay, so this is 0, 1, 2, 3, 4. Okay, 0, 1, 2, 3, 4. You add all 5 of them together with equal weight, you become 0. Okay, and from here we can so you write down from here we can derive something a bit more general. That's this expression. So you sum together a whole bunch of those e to the 2 pi jk over n, okay? And then you fix some k, then this will always equal to 0 when your k is not equal to 0. Okay? And here this expression is a bit complicated because well you have ijk here, but ijk are all different things. Okay? And so you have ijk here, but ijk will have a very different meaning here. I is, you might think it's just ijk, but I is complex I, so I is totally different from jk. I is the square root of 1, minus 1. Okay? And then you have j. J is a dummy variable going to be summed over. Okay? So in our example here, so we have j is this 0, 1, 2, 3, 4. Okay? And k is an arbitrary number. K is another dummy variable. K is a number you can choose here. And so different k will give you actually different result sometimes. Okay? And so when so in our 0, 1, 2, 3, 4 example, we have k equal to 1. Okay? So when k equal to 1, we are summing over 0, 1, 2, 3, 4. Okay? And I guess then let's see different things. So we have k equal to 1 is this, but when k equal to 0, now we are talking a little bit of signal and processing, but I think it's okay. But when k equal to 0, then you have all this power going to be e to the 0. So those are all equal to 1. Then this summation will equal to this summation omega equal to 0 will just equal to n. You are summing over n different 1. Okay? And so we have k equal to 0 is n, and k equal to 1 this is 0. And what's interesting is all other non-zero k will also give you 0. So you have k equal to 2, then you are actually summing over 0, 2, 4, 1, 3, and you see that you have still each one of them is summed to 0, and k equal to k equal to 3, then you have a 0, 3, 1, 4, 2, and then k equal to 4, you have 0, 4, and 8, 12, 16. Okay, and you can kind of see it from here. So for different k, you are just summing over different column or different row here. Okay, and you see that the first say you're summing over different columns, or you sum over first column is summing over a whole bunch of 1, it becomes just 4. But you sum over this column, this column, you're summing over this 4 point, it becomes 0. And you sum over this column is some 1 minus 1, 1 minus 1, it becomes 0. And you sum over this column is 1 minus I, and minus 1I, and it will also become 0. Okay, so summing over all column or all rows, then it's always going to be 0, except you are summing over first column or first row. Okay, this is just how Fourier transform is set up. Okay. And because we have this nice property, or also a bit of notation, so omega means we will write omega as a shorthand for omega sub n, which means e to the 2 pi divided by n. Okay, and from this you can easily show that if you apply Fourier transform on vector that's all equal weight, so 1, 1, 1, 1. Then you will get the square root n on the first element of all count and all 0 otherwhere, because the square root n basically corresponds to this k equal to 0, and all those 0 will correspond to all those k. And and that's one thing. And another thing is, well, you can have some element. So you have a 0, 1, 0, 0, 0 applied by your Fourier transform, and basically you are picking out the second column, and the second column will be the 1 omega square, etc. Okay, so that's some example of what happens when you apply Fourier transform. And let's talk a little bit about actual signal processing. So why people like a Fourier transform? what people like Fourier transform is you can transform your signal between so-called time domain and the frequency domain. So basically, when you have a sinusoidal signal, and so this signal we write it as a sine function, but it should really be e to the it should be e to the I theta, or I should say, this function should really be omega to the x. I think this is time domain function, so it should be, I guess, e to the I omega t function. Okay, and anyway, so if you have like a sinusoidal signal, but actually discrete signal, so we think okay, so we have this signal representing, we are saying this vector we represent it as a signal, so we have plot the x0, x1, x2 all the way to xn minus 1 here, etc. Xn minus 1 and the x0 here. So we have this kind of sinusoidal signal, and you do Fourier transform, then it will become just concentrated on one location. So for example, we have this very very constant sinusoidal, then it will become just 0. Okay. And then you have a higher frequency one. So for example, this one then will become just 1. So this one corresponds to, I guess I should write down a vector. So if your vector is 1 omega square and omega cube, etc., then you apply Fourier transform, then we'll get the 0, 0, 1, 0, 0 vector. I think, let me see. And it's basically this in inverse. Okay, but I think I might miss some minus sign. But anyway, should be okay-ish. It's probably omega. If I do omega minus 1 instead, okay, it's a bit complicated. So control 1, control P, and so I should say actually there is a bit of inverse here. So if I have this signal actually 1 and omega minus 1, omega minus 2, etc., and you will transform to this 1 because it's inverse of this thing here. And then you have a higher oscillation signal, you will give you you will say the frequency component is the higher one. Okay. So that's kind of the idea of a discrete Fourier transform. You will tell you what's the frequency of your signal, and you can also do other way around. So and you can do very similar transform to have some signal in frequency domain. Say you have some component on some frequency, and you will transform back to some linear combination of those sinusoidal. Although we are writing sinusoidal, but actually we are thinking about e to the I theta, because we are kind of better at plotting complex number. Okay, but anyway, those are some extra things about Fourier transform. We just need to know, for now we just need to know it's a very important transformation you can do, and it has a lot of mathematical application. And anyway, what we really need to know is how it's defined. It's defined this way. It's a matrix with its kjth element with kj index from 0 to n minus 1, being this 1 over square root n e to the 2 pi jk divided by n. Okay, and so that's a discrete Fourier transform, and there is some property that this is literally an important property, and I will ask you to show in homework. It's not too hard. You can show the inverse of this matrix. Okay, so inverse of it is very similar. It's just its element is basically the same thing, but you put a minus sign on the exponent here. Okay, so you can just do matrix multiplication, and basically you use this property, and you can show that Fn times Fn minus 1 equal to identity matrix. Okay, And so that's the classical discrete Fourier transform, and now we are going to generalize this to quantum Fourier transform. And the generalization is pretty straightforward. So we have input output vector and output vector, and we are just going to say the input and output vector are now quantum states. Okay, and so we want to define this quantum Fourier transform is a linear operation that take an input state and apply fn and give you some output state. Okay, so and so I guess kind of in this way, in quantum mechanics we are. I guess this definition is more natural. You have some computational basis element, and then you do your operation. It should give you some quantum state. Okay. And I guess so we do this definition. We can define this is a linear transform, but we want quantum Fourier transformation to be a very quantum operation. Then an important thing to check is that the quantum Fourier transform is unitary. So you need to check that. So we have this Fn matrix. You need to check Fn times Fn dagger equal to identity. And once again, this is something you can check in your work, but it's basically same question as this Fn minus 1 question. Because easy to see that this is Fn dagger. Okay, so it's a unitary. So if you just think about all the input and output are quantum state, then this Fourier transform matrix is just a matrix of unitary operation you can apply on quantum computer. Okay, so now this is a quantum Fourier transform, basically discrete time Fourier transform, but just think of this matrix as a unitary operator acting on some n-dimensional Hilbert space. Okay. And we have H matrix element just like before, 1 over square root n e to the 2 pi jk d pi by n. Or I guess the nice form we always want is 1 over square. Anyway, 1 over square root n omega sub n to the jk's power. Okay, and in terms of more direct application, we can say you have computational basis J will get mapped to this 1 over square root n. Okay, so now this is corresponding to I guess it corresponds to nothing. Okay, but you can do matrix multiplication, then you see that the computational basis J on it. Computational basis J will get mapped to this sum over different K. And e to the 2 pi jk divided by n. And let's see, maybe a bit of example to make this formula a little clear. Okay, so you think about you multiplying on those matrix with a computational basis, then basically you pick out some column. So say you pick computational basis 0, then you will pick out the first column, so it's O1. Or the computational basis with with coefficient 1 adding together. And say if you have a j equal to 1, then you will pick out actually the second column here, then you will pick out this column or this column or this column. So this will be 0 plus omega 1 plus omega squared 2, and here is similar, 0 plus omega 0 k to 0 plus omega k to 1 plus omega squared k2 plus omega cube k3, etc. And so you have j equal to 0, j equal to 1, j equal to 2, and j equal to 3 here. Okay. So that's the output of your Fn. Okay. And you write down it as an algebraic expression. It's this thing, e to the 2 pi jk divided by n k. Okay. And and then other way to see, and then you can take a linear combination of this and think about what you have general combination of input, and you will get some output. Okay. And so general combination input, so xj to yk, and now this formula is what we've seen before. So yk will equal to this inner product between xj and the and once again here k is different from j. So we write here, so k is something fixed. So k here, So yk will be inner product between the case row of fn and case row of fn and your x vector. Okay, so you see that you will sum over those j, and you have xj inner product with the jth row, which is this e to the 2 pi I jk divided by, inner product with the kth row. So you have dummy variable j here and this fixed k here. Okay, and and this expression is same as it should be same as this expression here. Yk equal to this summation square root 1 over square root summation j xj e to the 2 pi jk divided by n. Okay, and okay, go back. So we have a different interpretation. Now this discrete Fourier transform is a quantum Fourier transform. Okay, any question? Okay, so we are going a bit fast. And if all okay, then okay, so then we are going to construct a circuit to do quantum Fourier transform. So what's good about quantum Fourier transform, why people like it, is because on quantum computer you can do quantum Fourier transform much faster than you can do discrete Fourier transform on classical computer. Okay, and so now let's go to the hard part, and let's try to construct our phase quantum circuit to do quantum Fourier transform. Okay, and okay, so now it's going to be really tiring. Okay, and so before we even start, let's set up some notation. And the first thing we do is we make our problem a lot easier by restricting our n to be power of 2. Okay? And if n is not power of 2, then there is something you can do. We'll skip that. But ideally, you can kind of have a bigger n and scale down. Okay. And so here we restrict n to the power of 2, so makes things a lot easier. And bigger n is 2 to the small n. Okay. And and we will do some notation here. We will identify bit string. Okay, so so before we have a whole bunch of things counting from 0 to n-1, because our bases are 0 to n-1, and instead of 0 to n-1, we are going to break them into bits, because we have this n equal to 2 to n thing. So identify 0 to n-1 with n bit strings, 0, 1 to the n, and it's just the binary representation identification. So for example, 0 is the O0 string, and n is n-1 is the O1 string. And but we are going to see in dirty details or C detail. So some number from j from 0 to n-1 we'll express it as this bit string. So j1, j2 to jn, and it's just basically a binary representation of j. So it's j1 to the 2 to n-1 plus j2 to the times 2 to n-2 all the way to jn times 1. Okay, and okay, so here is an example here. So maybe our n small n equal to 3, big n equal to 8, and we have this 6, which equal to 2 to the 2 plus 2 to the 1, and we write it as this 110 string. Okay, so this is just a binary representation. Okay, binary representation you should be all quite familiar. And now there is something that you might not be familiar. So we also have this binary representation for fraction. Okay, and so now this is slightly confusing. So you have 0.j1, j2, j3 to jn for some length, and this is just we can also have this binary fraction. So this is j12 times 2 to the minus 1 plus j2 to the times 2 to the minus 2 all the way to jn times 2 to the minus n, and all summing together. Okay, so this is just a binary, just a fraction in terms of binary. Okay, so for example, you have a decimal 0.75 is 2 to the minus 1 plus 2 to the minus 2. So in terms of binary fraction, it's 0.11. Okay, and we'll denote binary fraction with this bracket. Okay. And hopefully, yeah, for now, yeah, we should do the fraction all nicely. Okay. And yeah, so we have those binary binary counting symbols, and now we try to do this quantum Fourier transform. So first is we are going to factor, I think it's this expression. Okay, and yeah, so here is the we have about 10 more minutes, so I guess we can try to finish this class. So this is a very technical class. So quantum Fourier transform, we want to do. Oh, okay. So actually, the one we change is this one. So we want, because we know we have this one, then those are three equivalent things. So we have this thing, then we have this thing, and then we have this thing. Those three statements are equivalent. Okay. And we start with this one because just because I think you can work with anyone. But this is cleaner because it works on computational basis. Right? So we want to see how we want to engineer how each computational basis is mapped into a quantum state. Okay, and so we have a J mapped to some K, but we have because basically we want to do very careful bitwise get a bit. We want to do get qubit by qubit, so I want to put this J and K into binary representation. So we know that how each qubit should be acted on. Okay, so let's put J and K into binary representation. Then we see that. So first we have a J equal to binary representation. Here we have a J, and we say that J is something from 0 to n-1, so it can be put in binary. So it's just this J1, J2 to Jn, and it should be J1, J2 to Jn on each qubit will represent our computational basis J. And then we'll get mapped to actually this tensor product state. Okay, so we have n bit input, and you should also map to n bit output because the input and output number are the same. The input and output dimension is the same for this unitary transformation. And they all have this big N equal to 2n, and so you have this NB input, which is a product state. Then we see that even though we have this seems like a quite complicated transformation, when your input is a bit string, then the output is actually a product state between each qubit. Okay, and it's this thing where each qubit looks kind of like a plus state. So each qubit has is equal superposition between 0 and 1. So you have K0, K1, K0, K1. But you have this really weird phase on each qubit. So you have e to the 2 pi times now some fraction. Okay, so you see now this binary fraction number here. Okay, and this binary fraction is exactly this notation here. Is the 0.j something notation. And on first qubit we have this fraction here being 0.jn. So remember jn. So this jn is n jn on input. And on the second qubit, you have 0.jn minus 1 jn. So the last two bits here. And yeah, so you add 1 by 1 all the way to this being 0.j1 to jn. Okay. So this is like a factorized expression for quantum Fourier transform. Okay. And I guess with 8 minutes, I'm not sure we can complete a proof. But let's try to start a little bit. But before we start trying to show the proof, any question what this means? This is another expression for quantum Fourier transform. Just but for this is for n being a power of 2, and we map it into this bitwise expression. Okay, and also there is this normalization here 1 over 2 to the m over 2, but it's not too important. Just remember there is a normalization. Okay. And yeah, okay, if you are okay, then let's try to complete the proof before we go to break. Okay, so the proof, here we have a notation, so we will write this kind of thing. So this is tensor product, and we write I from something to something, and some function of I. And this is tensor product, so this is a whole bunch of things tensor product together. So for example, so that's because you don't want to write a dot 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 here. So this is writing a dot 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 with more complex notation. Okay, just a whole bunch of string of tensor product. Okay, and yeah, with the notation in mind, let's see. So we start with our starting expression. So j to some summation of k, j to summation k from 0 to 2 to the n minus 1, and e to a 2 pi jk over n and k. And big N is 2 to the n. So now big N is all those 2 to the n. Okay. And let's see what the first step we do. First step we do is we just write I guess k should also be red. But anyway, first thing we do is we'll break this k into also binary notation. Okay, we want to write k also in this thing, and yeah. Okay, so k is something. K in terms of qubits is k1 to kn thing. Okay, and now this summation k. Oh yeah, I guess here I should also highlight this k here. Okay. Anyway, this summation k, k from 0 to n minus 1 is well, just you can just sum over each individual bit. Each individual bit is 0, 1, and that's the same as sum from k. K is from 0 to n minus 1. That's just the same thing. And then we also need to break this k here. Okay? And we have this k divided by 2 to the n. And now I think about this, this is actually equal to summation KL. Okay, and here we have another summation L. So L is the index for this 1 to the n here. So basically we are writing down this summation because say here J we have J1 times J2. So we are basically just writing down this dot 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 as a summation. Okay, so we have k. Let's write this even slower because it's quite complicated, but it's actually not too hard. So k equal to k1 times 2 to the n minus 1. Let's see if I do this correct. Plus k2 times 2 to the n minus 2 plus dot 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 plus kn times 2 to the 0. Oh, where am I? Okay. 10 times 2 to the 0. And if I write this dot 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 as a summation, then we need a dummy variable for this 1 to n. So it's just summing over L from 1 to n. And you have 2 to the n. Oh, so we should have our k. So we have our KL and times 2 to the minus L. Okay, so this is just expressing k as a binary as each summing over each bit and 2 to the some power. And yeah, then we divide by 2 to the n, then you get rid of this n, then so you have this summation L, KL 2 to the minus L. Okay, and then with this thing, then now we use our tensor product notation. Okay, and yeah, because now we see that this expression has a very nice form. It's already kind of in tensor product. Because you have this summation on your exponent, then you can put summation exponent. You can just have the product of all of the instead of summation exponent. You can have the product of all the exponential. right? Because you have basically here we are using e to the a plus b plus c plus da 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 equal to e to the a times e to the b times e to the c da da da. Okay, and so here is we use this. Okay, so we should have we skip 2 steps. So first we should first break this into product of a whole bunch of exponential, and then we see that so once we so inside this summation. So if we don't move this summation yet, so inside this summation we have this product of exponential, and then we also have the product of state here, because this is well, computational based state. It just each qubit is 0 or 1, and so you can just match together each exponent with corresponding qubit here, because each of these ABC term will only depend on one of the KL. And yeah, so now we have a tensor product of state here. So you have each qubit will be the KL that's indicated here, and with the phase vector, that's this e to a 2 pi j, and times this KL 2 to the minus L. Okay, and yeah, we have this thing. Okay. Then from here, let's do next step. Okay, next step we change the order of doing tensor product and summation. Okay, and we can do this because this summation kind of how to say, this summation is separated out. So because in the tensor product, each term only depends on one L, and also see the summation here, each summation only sum on each KL. Okay, so instead of tensor product together and then do summation, you can tensor product together and do summation. You can pull the summation inside tensor product, because each of the summation only affect one of the tensor product here. Okay. So the tensor product are like all those slots here, and yeah, so we put a summation inside, and but actually from here we'll kind of already see this, but we are just write it in more explicit form. Okay, so we already the tensor product and the summation. Now we put the summation inside tensor product. So yeah, so we have a tensor product L from 1 to n, and we sum each KL from 0 to 1, because we have each KL here. Okay. And now just write this out, then we immediately see that we are getting this thing. Okay. So sum KL from 0 to 1, and so KL 0, then you get K0 here, and this thing here will be e to a 0 will be just be 1, because you have a KL here, so that's mark KL. KL will be 0 and 1, and KL 0, obviously you have e to a 0, it will be 0, and KL 1, you have e to the 2 pi j and 2 to the minus L. And yeah, and this thing will just be the expression that we claim that we want. And we are going a little over time, so let's take a 10-minute break, and yeah, then we will finish this proof here. Show that this expression is actually all those things. Okay, yeah, let's take a 10-minute break. 我觉得已经够快了，应该不会怎么费事对。我就把应该是把 QMT 讲完差不多。对啊，应该是10就好。
刚删掉了一个符名，不知道为什么要出现那个
rotate 是什么？我看一下，我不知道为什么出现啊。有宁愿看错。
原来这是这个。
这个，哦，这个是很久以前的，这个是之前 circuit 的吗？这应该有之前在出的。这个应该是很久以前的作业，忘了出了吗？
我没有很懂为什么开着。
那你可以把它丢到前面，那你先把它，你再把它搬到前面，把它就是后几年的 file 那个。前面我们出过它吗？我忘记了。前面忘记出它是不是？还是因为考到期中考的关系？不太确定。感觉应该是期中考前要出的。的确是，刚讲方程式 K 的时候，那就有讲。
其实也是可以把它
对，让它出现，比较混乱。然后如果你找不到题目的话，就出它吧。Okay. Okay, let's get back to our quantum Fourier transformation. Okay. And yeah, as we say, we want to prove this very nice form of quantum Fourier transformation. So how it acts on computational basis state when your big N is 2 to the N. And we are going to prove that it has this very nice product state factorization. So all those 0 plus 1 tensor together with different phase. This e to the 2 pi I and 0.j1, 0.jn, 0.jn minus 1jn, and 0.j1, j2 to jn. Okay, and what are all those 0.jn etc. things? And we see that to our derivation, we see it's actually j times 2 to the minus l. Okay. And so what is j to 2 to the minus l, those 0.j something, because basically it comes from e to the 2 pi equal to 1. Okay? So if if we have integer here, then we see nothing. E to the 2 pi times any integer is just 1. It's like equal to e to the 2 pi e times 0. Okay? So basically, when we are multiplying with e to the 2 pi here, this number or the integer part doesn't matter, so we can just cut it out. Okay. And yeah, so then we think about this. What's what is j times 2 to the l in terms of binary? So j is j1, j2 to jn, and then divide by 2 to l. Then you are just moving the decimal number. This decimal dot, or I guess it's not decimal. This binary dot. You're just moving this binary dot in front to the front by L unit. Okay, so you just have J1, J2 to J to the n minus L minus 1 dot this J n minus L and all the way to J. And I guess it's easier to see an example. So for example, if L equal to 1, so you start with a J, which is J1 to Jn, then you move this dot in front of 1 unit. Then you have the J1 to Jn minus 1 dot Jn. Okay. And but as we say, all those J1 to Jn minus 1 doesn't matter here. Then so we just write it as a 0, and you just have 0 dot Jn as the first element here. Okay, because because e to the 2 pi times any integer is to any integer power is still just 1. Okay, and yeah, so when L equal to 1, you move the dot by one dot, you have 0 dot Jn. Then on next one, you have L equal to 2, so you move this by 2 units, then you have 0.Jn minus 1 Jn, and yeah, etc. all the way to next one. Then you have a dot in front of your J1, so you have the 0 point everything, 0 point J1 to Jn, so kind of a 0 point J. Okay, so that's the quantum Fourier transform expression. Okay, and yeah, so this expression is actually quite well known already known in classical words. Okay, and yeah, a bit of a digression. So this is the basis of how people do classical Fourier transform. Also do I guess the so-called phase Fourier transform. Okay, and yeah, so this decomposition will written it in terms of this tensor product and the quantum, but really you can also think this in terms of just the classical matrix multiplication. Okay, but yeah, that's something else you can study. For now, we are going to use this to do a quantum circuit. Okay, so we have this expression of quantum Fourier transform. And finally, now we have the efficient circuit for quantum Fourier transform. Okay. And yeah, here is the circuit. So we have input x1, x2 to xn, and we want the output to be those weird things. Okay. So we have 0, 1, 0, 1, 0, 1 on everything, and with 0 plus 1 on everything with this weird fractional factor. So this is 0.j1, 0.jn, 0.jn minus 1 jn, etc. But we copy the picture from Wikipedia, so instead of jn, we have xn here. Okay, and yeah, so what we do is we will have do this circuit. We can this circuit will give us this output, but the ordering is reverse because we have 1 to n here, and this is actually this is actually the first one here, and this is the last one here. So after we do a circuit, we also need to reverse the order with a whole bunch of swap gate. Okay, but yeah, the thing about swap gate for later. The important part is getting all the weird phase. Okay, so how we get a weird phase is we'll do whole bunch of headma. So you can probably feel that you need a whole bunch of headma because you want all those 0 plus 1. So all those headma will give you 0 plus 1, and headma give you 0 plus 1, and you have a whole bunch of control rotation. Okay, so what are all those control rotation with some very small phase. Okay, so this is this is similar to some rotation around the axis. But anyway, it's this gate is when it's a control. I guess it's a control phase. Sounds a little weird, but anyway, it's a control on the control qubit. You apply some phase on your target qubit. So control is 0, you do nothing, and control is 1. You apply this exponentially small phase. So it's e to the 2 pi divided by 2 to the k. And here k is indexed here, so we can have a k from 1 to small n. And yeah, so this gate is is actually a family of gates. It's indexed by this k, and the phase you apply is exponentially small in k, so it's e to the 2 pi divided by 2 to the k. And once again, k is yeah. So once again, k is in this 1 to n range. So I should write k is 1 to n, so I can write this thing. Okay. And yeah, so yeah, basically those RK will rotate those small fractional phase up here. Okay. And let's see how this works out. So we can do this qubit by qubit. So basically, the first n gate here will give you this thing. Okay. Let's see. Yeah. Well, let's see how this works out. Apply Hedman first qubit. Okay. And yeah, so let's see how this will go one by one. Okay. And we have J2 to Jn, and let's see how first qubit get transformed. So first you apply this Hedman here, okay, and Hedman give you 0 plus 1. Okay. And 0 plus Hedman give you actually not 0 plus 1, 0 plus minus 1 to the x1 1. Okay. Because J1 equal to 0, you have 0 plus 1, and J1 equal to 1, you have 0 minus 1. Okay. And 0 times minus 1 over 1. Okay. And here we are ignoring all the square roots, so it's a bit easier to write. Okay. And yeah, then you can combine those two expressions into next expression of is e to the 2 pi times and this minus 1 is e to the 2 pi times 0.5, or in terms of decimal is bracket 0.1. Okay. And yeah, so it's e to the 2 pi. Yeah. So yeah, so if you combine those possibility, it's e to the 4 pi and the bracket 0.j1. So when j1 equal to 1, you have this 0.1 here, and j1 equal to 0, then obviously you have nothing. Okay. And so you get 0.j1 from just the Hedman, and then okay, so you have 0.j1, then you want your 0.j2, and 0.j2 you get from control on x2 and do R2. Okay. And yeah. I guess it's how to say, so when J2, so you see, because it's a control on x2, sorry, x2 is J2. It's very confusing here. So remember x are all J. Maybe let me remind myself. So this is J1, J2, and J3, etc. Okay. Jn minus 1 and Jn. Okay. And okay, so this is control on J1. So Hedman on J1, you apply 0.J1, and control on J2. Now you control on J2. So when J2 is 0, then nothing happens. You still get this thing. And J2 equal to 1, then you see that where we wanted this small fraction. Okay. So we have 2 to the 2 here because we are doing R2. So J2 equal to 2, then we'll apply e to the 2 pi divided by 4, and that's basically e to the 2 pi 0.01 in terms of binary binary fraction. Okay. And yeah, so when J2 equal to 1, you get the extra 0.01 vector, and they add together with this 0.j1 vector vector, so you get 0.J1, J2 vector here. Okay, and yeah, you can see that you do one by one because you have this exponentially smaller and smaller fraction, and so your control will give you exponentially smaller correction. Then you have a control on J3, do this 0.00J3, etc., and all the way to Rn, you get this 0.J1, J2 to Jn on your one. Okay, so first qubit will become this thing. Okay, and the first qubit becomes this thing. So nice thing about kind of the idea of using this expression is you see that only the last qubit depend on J1. Okay, because you get those phase expression is shorter and shorter. Okay? Only last qubit depend on J1, so you can just transform J1 equals this thing, and then you can do J2, because now you cannot access J1 anymore because the J1 qubit got transformed to this thing. But all those things doesn't depend on J1 anyway. So now you just do on J2. Okay. So similarly, you do Hedema, you get 0.J2 here, and you do all those control rotation and get all the following thing. Okay. Okay. So you can do Hedema on the second qubit, get 0.J2, and all other thing, and on the second qubit, then. And yeah, so on the second qubit, you need to control on all the third to nth qubit, and in the end, you will get this phase. And once you get this, you see that all those things doesn't depend on J2, so you can just continue with this thing. Okay, continue with this cascading control, and yeah, and in the end, you will get going through all qubit, you will get this expression, and you just need to reverse all your qubit to get your quantum Fourier transform result you want. Okay. And yeah, I guess here we can say so after you do this, then you can say that maybe here. That the 2 to n qubits does not depend on J1. So you can just transform the J1 qubit to what you want and forget about it. Okay. And yeah, so that's the circuit for quantum Fourier transform. You do n gate to transform your J1, then you do n-1 gate to transform your J2, then you do n-3 gate, n and n-1, n-2, etc. And all the way to Jn. Jn only need to do a Hedema, just one gate. Okay. And yeah, and in the end, you need to do a whole bunch of swap gate to reverse the order here. Okay, and here we see quantum Fourier transform in some example. So with only 3 qubit, n equal to 3, and small n equal to 3, big n equal to 8. Okay, and want to do Fourier transform on J1, J2, J3, and it should become, the result should be 0 plus 0.J3 on 1, and then and 0 plus 1 with this vector 0.J2J3, and then 0 plus 1 with a vector 0.J1 J2J3, and the circuit will look like this. Okay, and so you will try to do this 0 and plus this 0.J1 J2J3 one first. So you need to do Hedema on J1 and control on J2, rotate with this 1/4 angle, so get this J2, and control on J3, get this 1/8 angle, get this J3 here, and then things don't depend on J1 anymore, and then you do the second one, then you do Hedema, get this J2, and do this R2, get this J3 here, and finally you do Hedema, get this 0.J3. And in the end, you do a swap to swap the order into the same order as what we want. Okay, And yeah, so we're almost finished today. I guess we can, we still have quite a bunch of time, but we talked enough. So I guess we'll have our next slide here being the quantum Fourier transform. Okay, and yeah, so let's count a little bit of how many gates we use in quantum Fourier transform. So we have order n squared control rotation plus order n swap gate. Okay, order n squared control rotation because we have n plus n minus 1 plus all the way to 1. So that's order n squared. And yeah, at the end we need order n swap gate. So totally is order n squared gate. And that's order small n. And in terms of big N, that's order log square of big N. Okay, and now compare to classical Fourier transform. So if you have a vector, you want to calculate a vector of big N dimensional, and they want to calculate this Fn of V. And classical computer, you need to do theta n log n. Okay, yeah, you need to do theta n log n, just elementary operation, multiplication or addition. Okay. And yeah, this is so-called phase Fourier transform, and you use a very similar decomposition to this thing, but well, with a different notation because in classical computation you don't write gates. But yeah, you can also do a recursive calculation that only require order n log n, multiplication, addition. And if you do this in stupid way, then if you just do direct matrix multiplication, then you need order n squared. So this is still faster. But you see that quantum Fourier transform has quite a bit of speed up. So it has so-called exponential speed up because quantum Fourier transform only need order log square n log square n operation compared to classical you need theta n log n. Okay. And well, you just compare these two numbers, you see that this number is exponentially smaller than this number. Okay. But catch here is quantum Fourier transform don't actually do classical Fourier transform. So you cannot use quantum Fourier transform to do classical Fourier transform because you are transforming a quantum state, you are not transforming a classical vector. Okay. So you have some classical vector as input, and then you want to compute it as a Fourier transform, then yeah, even on quantum computer you cannot do with this thing. Yeah, so it's an important concept to know. So quantum Fourier transform cannot do classical data because doesn't work on classical data, it only transform quantum state. Okay. And yeah, I guess we have time, so we can say a little more here. That's right, maybe here. Okay, so I guess the biggest thing about this is okay. So assume so you have some classical vector x. Okay, so you have some vector x here as an input, and assume you do some normalization correctly. Okay, so you can think about if you are lucky, so. Yeah, so I guess here I want to talk about the problem with quantum Fourier transform. Okay, so the problem is input-output. So you have this x, and so classically you have a very strong lower bound to do Fourier transform being order n. That's just you want to read through your x with x as n entries, and they just looking through all your data, you require like a order n operation because yeah, just read all your data require order n time. Okay, and yeah, so that's just much longer than you try to access this quantum state which has only small n qubit. Okay, so you have classical data, you have n qubit here. N bit string here, then well, you need n time, bigger bit string, then you need order n time to not even order n time, you just need n time to read all your input elements here. Okay, and but even assuming you have somehow given a state that's corresponding to this vector, so say you have some quantum state of this vector, and you can do quantum Fourier transform, right? You can do in our notation it's do we have a name for? I guess we write f. Okay, so we can apply. You have this set, and you can apply fn of x. Okay, you get fn of x, and you get this vector, and it's still different from you get the classical y vector. Okay, so here is I guess a bit back to information theory. So remember, so you are given just this vector as a quantum state, but this is basically given to you as an unknown quantum state. So you have this quantum state, but you take a lot of time to, and even a lot of copy of this state to learn each element of this quantum state. Okay, and yeah, so even though you can do quantum Fourier transform really fast, and you get this output state that's kind of correspond to your classical vector y. So now you get this quantum state y, and but this quantum state y, you want to get the classical vector y, then you are hit with this quantum information barrier where you have a unknown quantum state. You want to learn it, then you actually need a lot of time and copy to actually learn your quantum state. Okay, so even though so bottom line is go back to what we really want to talk about. You can do quantum Fourier transform really fast, but you cannot use the quantum Fourier transform to do classical Fourier transform, because even if because you have a lot of problem in your input and output, so you need a lot of time to read your input to create the input state, and even if you have the input state, then you get this quantum Fourier transform output state, then you cannot read this output state as a classical vector out. Okay. So that's a big catch about quantum Fourier transform. Okay, but quantum Fourier transform is still nice, and people do use it to do also a lot of things. And in particular, a very nice thing about quantum Fourier transform is that we are going to see that the quantum Fourier transform allows to do factoring much faster than what the classical computer can do. Okay, and yeah. It will stop early, but show you a little bit extra. So yeah, next time we are going to talk about phase estimation. So this is something very quantum thing you can do with the quantum Fourier transform, and this will be the basic of how we do factoring. Okay. And yeah, so I guess a bit of spoiler, so phase estimation is a quantum thing because you are going to give, okay, now we are going to basically get back our black box. So we have unitary given us as a black box, and we want to estimate its eigenvectors. Okay, so that's phase estimation, and we are going to see that quantum Fourier transform let us do phase estimation. Okay, so yeah, that's what we do on next Tuesday.